So now we're going to look at the Everlasting Options Greek modeling tool set. So the first thing we want to do here is basically pick out the asset. In this case, the asset is a little bit arbitrary because this is theoretical modeling. But let's say we pick out Bitcoin and we're looking at a $100,000 strike. We go ahead and hit calculate. This will kind of line that up. And now there's a few things to look at. Here we have a slider that shows us the underlying price. So right now we assume that we're at the money. So we're at the strike price, exactly $100,000. And let's look at a call actually. And then the frequency is again going to be set to 1 day. So that's sort of the standard everlasting option where there's a daily expiration for each underlying portfolio of the composite, or each option of the composite underlying portfolio. But you could theoretically change that. So let's say you picked out 6. Well, the first option would be 6 days out. The second option in the portfolio would be 12 days out. The third, 18, so on and so forth. But these would still roll sort of every day. But we'll go ahead and stick with the 1 day option. And here, because we're using N of 9 or 9 underlying theoretical options, we can go ahead and adjust the volatility curve to however we see fit. So let's say we want a hump shape term structure. Now I can go ahead and do that. I hit calculate. And now I have, basically this is my everlasting option Greek profile. And here I have the distribution of each option to that total Greek profile. So we can see that the first option in the series, which has a weight of 50%, sort of dominates the Greek profile. And then the second one has less, and so on and so forth. But we can basically see how each one lines up. So we can see, for example, that the theta, 60% of the theta comes from that first option. Whereas most of the gamma, 60% of the gamma comes from that first option. Whereas option 4 provides 12% of the rho, for example. And what's great here is we can see how this shifts. So let's say we go slightly out of the money. So let's say we drop 15% in the underlying. What happens? Okay, well now we have a very low delta. Our theta has decreased as well, and we have a low vega. And now we can see that those first few options, the second we're out of the money, those first few options lose so much of their value that they almost have no more impact to the Greek profile. And now the Greeks are sort of dominated by these tail options in the distribution. Now, how does this change? How does this change with a different volatility environment? So let's say we pump up vol to 200 for these first 3 options and then calculate this thing again. Boom. All of a sudden, because volatility is so high, it doesn't even matter that we're 15% out of the money. These first few options now have so much volatility that they're basically, at the money again, and their Greeks are the ones that are important. And theta has gone up a lot. We can go ahead and pump up theta. Let's go back to at the money and keep the same implied volatility profile. Boom, theta is so big, which makes sense, right? Options that have a lot of implied volatility are very expensive. Therefore, their theta grows as well because they still, decay, but there's now more value to decay, so to speak. Let's go ahead and see what happens when we go into money. Say we're into money 10%. Okay, bam, delta is 80%. Theta has reduced. Makes sense, right? Because now when we're at the money, we're 100% extrinsic value to these options. And once we're in the money, there's less extrinsic value and there's more intrinsic value. Now we can see the deltas, 50% of the delta comes from that first option. And the theta, most of the theta comes from that first option, so on and so forth. So this is the modeling tool to sort of gauge what happens in different volatility environments as the Greeks move around. We find this very useful to help traders and users wrap their heads around the different Greek effects in different volatility environments.